we're just going to sort of hang out. I told you about my dog. He's passing away, so we're just trying to be home with him and, take every moment that we can with him, because he's an awesome dog. He's like the best dog that we've ever had. That's my neighbor. What do you think? Good dog? Okay, so vectors. We've already seen vectors a bit, or we've talked about vectors, and that is that they have a magnitude and a direction. We talked about some different vectors: velocity, acceleration, and displacement. And that those are different from speed, for example, and distance, because those only have magnitude. Speed and distance, for example, would be a scalar quantity, and they only have magnitude. So speed, distance, time, mass, etc., etc. Energy is a scalar quantity. We usually draw vectors with an arrow. So for example, if we have the velocity, we'll usually draw an arrow over it. So like I told you, I get a little lazy with that when we're doing kinematics problems. Acceleration would be like that. When we get into forces, we'll draw it with a little arrow over it. And we represent a vector graphically like this. Now in this, on the exam, you'll have to know how to graphically add vectors and how to numerically add vectors. And we represent a vector graphically like this. We get an arrow, and it has a certain length, and it has a certain direction. So the length of this arrow gives the magnitude. While the direction is given just by the direction that the arrow points. All right, so for example, if I have one vector that's bigger than another, say if I draw a vector like this, and I'm going to say that this is a displacement vector, and it represents a displacement equal to 1 meter. Then I would draw my vector to be, or at least to represent 1 meter. So I'm just going to say that this represents 1 meter. You would actually wouldn't draw the vector 1 meter long, because a 1 meter vector wouldn't fit on your page, but you would have a scale. And in fact, in one of the labs, you're going to be doing this. It's kind of a fun lab where you add up vectors. Listen, we're dealing with vectors a lot in the next 3 or 4 or 5 chapters. So you're going to see this a lot more as we move along. But in this first test, the questions are going to be fairly straightforward, and I'll show you sort of what to expect. But anyway, this vector has a magnitude of 1 meter. What if we were to draw another vector like this? What would you think would be the magnitude of that vector? Well, I've drawn the length, what, more or less? It's less, right? It's about half the length. It is half the length of that other vector. So then it represents a magnitude of the displacement equal to what? Wait, half a meter. So it'd be 1/2 meter. The direction would be the same for both of these. So the smaller vector in this direction has the same direction, but it has half the magnitude. Bless you. Of the larger one. So whenever we represent vectors, we let the length of the vector be correlated or be proportional to the actual magnitude of the vector. And then we'll let the direction of the vector represent the direction of the vector. The direction of the arrow represents the direction of the vector. May I go down? Yeah. All right. So two vectors are equal if their magnitude and direction are the same, but you can move them around any way that you want. So let's say that I have a vector that looks like this. I can take this vector and I can move it around in any way that I want. So I can draw it over here, wherever I want, I can draw that vector. And it's going to be exactly the same. So all of these vectors, as long as I keep the same magnitude and direction, are exactly the same. In fact, when I draw my coordinate system, I can move that vector around any way I want. Usually, I'm going to draw it like that. But I could draw it any way I want. I could draw it like that. I could draw it like that. However I want. I can move that coordinate system around. This will be really important in Chapter 4. It's going to be a little bit important in the next little bit that we do. But you can take a vector and move it around, translate it in space, as long as you keep the same direction and as long as you keep the same magnitude. So as long as you don't change their direction or magnitude. Okay, so we're gonna, on the test, you'll have at least one question that's dealing with the geometric method of adding vectors. And the way this works is that you place two or more vectors tail to tip. So you place your vectors, two or more, tail to tip. And so let's say that I have three vectors. Let's say that I have a vector A, say that I have a vector B, and then I also have a vector C. This is A, this is vector B, and this is vector C. And I want to know what is the sum A plus B plus C. In order to do this graphically, the way I would do this is I would take the vectors and move them around in space until I get them all lined up, the tail of one to the tip of the other. So I draw the first vector A like this. Then I draw the second vector, the tail of B to the tip of A. So it'll look like that. It's going to be B. And then I'll draw C like this. And then I'll connect the two. And that would be the resultant. I'm going to call this the vector R. So R is equal to the sum of the vector A, B, and C. Graphically, this is how you do this. You set up the vectors tail to tip. I put the tail of the second vector to the tip of the first vector. I always like to think of this as just sort of different paths of walking. If I start here, there are a couple different ways that I can get to my location. Right? I can have three vectors, one that takes me here, here, and here, or I can also start here and go here. Regardless, it's going to be the same displacement. Displacement is a nice way to think about vectors because you can envision it in your head. But I get to the same position. I've had the same change in position, my same displacement, but I can go by different routes. And so those are going to be equal, at least in terms of our vectors. Also notice that you don't add up, or you are not going to add up vectors A, B, and C. So for example, if this was 2, 3, and 1, you wouldn't just say 2 plus 3 plus 1 to get R. It's a little more complicated than that. You have to use your trigonometry. We're going to show you how to do that, which is also something that you need to do for the test. Okay, yeah. So consider two vectors A and B. We're going to sort of step through this, but I'm going to show you something different that can come up. So for my tail to tip, this is my vector A. This is my tip. All right, and I want to know what is A plus B. This is my vector B. This is my tail of vector B. So I'm going to place the tail to tip, the tail of the second, to the tip of the first. And then connect them. So it'll look like this. If I'm just doing two vectors, I would say A, and I would have B, and then I would connect the two to get the sum of those. R equals A plus B. And then if you're subtracting vectors, like let's say instead I wanted to know A minus B, what do you do to that vector that you've now negated? What do you think you're going to do to the vector that you've made negative? Well, let's think. So we've seen negative directions before. How are they relative to positive directions? What do you do to them? Like if positive is to the right, what is negative? To the left. Right, so if you negate a vector, what do you do to it? Flip that thing around, okay? So if I'm doing A minus B, for example, then I would take A, A is still the same. Negative B now is going to look like this. See how I did it? I kept the same distance, or the same length of that vector B as what I had up here. I just flipped it around. I basically just drew the tail and the tip opposite one another. And then if I want to know what R is, right here, R is equal to A minus B. All right? You can also do this for 2 or more vectors. And so we'll have a practice on this because you're going to have to do it for the test. Well, I'm going to give you 2 vectors. I'm going to ask you for the sum or the difference. Oh, and by the way, what if I wanted to do 2A plus B? Well, then I would draw vector A, but vector A is going to be twice the length that it was before. So I draw the vector A, that's 2A, rather, twice its original length. The vector B is that same original length, and then the vector R is equal to 2A plus B. Yeah. That's right, Gavin. So if I subtract a vector, I just switch the direction of it. All right. So here I was subtracting B from A. I had A minus B. Don't even think of it as subtracting. Think of it as adding the vector. And I'm negating this vector B. And so I took B, and normally it would have been drawn up in this direction, but then I draw it 180 degrees. It's a good question, and you will have a question like that on the test. I'll show you a similar one that you'll have in just a second. But you can do this also for 2 or more vectors. Like, let's say that I have, well, this is like what you'll have in lab, actually, where you have A plus B plus C. Those would be my 3 vectors. And then if I want to know the sum of those 3 vectors, I start at the beginning, and I draw an arrow towards the end. Often a mistake that students will make is that they might even draw A, B, and C correctly as they're drawn here, but often a mistake that they'll make is they'll start here and go up in this direction. But please remember that you always start at the beginning, at the tail of the first vector, and then you go to the tip of the last vector. I'll show you what I mean by that, because you'll have both options for your multiple choice, and just ensure that you're picking the right option. That is, this is the lab 3, I think, that you'll have for your 203 class. Okay, let's try this question right here. So I have magnitudes of A and B are 12 and 8. So that means that A is 12 units long and B is 8 units long. And if I know that A plus B equals R, what are the maximum, or excuse me, what are some possible combinations for the magnitude of R? Don't worry about this question. Sorry, this is a typo. We'll come back to it. But what is a possible value for R? No. I appreciate that. And you're sort of right. That is a possible value. But one of these is a possible value for R. Who said that? Akira, you were right in saying that the 2 vectors are perpendicular to one another. And so what she did is she used the Pythagorean theorem, right? Yeah. And that's correct. But you're thinking a little bit too much about this. That's not really what we're asking. But that's awesome. But here I have 2 vectors. One is 12 and one is 8 units long. What of these, 14, 22, 3, or 96, which of these is a possible solution for R? You want to think about what are the maximum and minimum values for R. How can those vectors be oriented so that you get a maximum value and a minimum value? What orientation of the vectors will give you a maximum value for R? What orientation of the vectors will give you a minimum value for R? And then your answer will be somewhere in between those 2 values. All right, let's stop in about 10 seconds. 220. Okay, good. A is right. Think about our maximum and our minimum. The maximum is I have my 12 unit vector in this direction and my 8 unit vector in that direction. And then the vector A plus B is going to be, well, 20 units long, right? That's the sum of those two vectors. What's my minimum value? How do I get a minimum value for these two vectors? What must be their orientation in order to get a minimum value? They must be opposite one another. And it doesn't really matter which is which direction. I'll draw the 8 unit vector here, or excuse me, the 12. So this is 12, and this is 8. And then if I want to think about, well, what is my resultant vector? It's going to start here at the tail of the first vector and go to the tip of the second vector, and that's going to be 4 units long. And so the answer is going to be somewhere between 4 and 20, which the only answer there is 14. All right? So it's not going to be like either one of these. In fact, it's going to be sort of more like I have my 12 and then my 8. And so the resultant would be like this. I would have 12 units long, 8 units long, 14 units long. Y'all will learn how to add up these vectors in the lab. In fact, we're going to do it too. I'm going to show you numerically how to add up these vectors. Let's try this question. You'll definitely have a question like this on the test. I have two vectors here, A and B. Which of these possible options is the result of the difference A and B? A minus B. So this is vector A, this is vector B. Which of these is A minus B? By the way, if it's unclear, this is A, B, C, D. The options. All right. Think about your vectors. Remember, you're doing a difference. So think about what happens when you negate a vector, and then do your tail to tip in order to find the new resultant vector. I want to redraw it. Okay, doing pretty well on this. I'm going to stop at 125. 125. Okay, good. So D is right. The reason it's D, A minus B, I draw my first vector, A. Then I draw my second vector, negative B. It's just like B, except I just switched the direction. And then the resultant, I start at the beginning of A, and I go in that direction, and then I just pick out the one that looks like that. You shall have a question like this. It'll be very, very similar. I'll just change the directions. It might be B minus A, or A plus B, or B plus A. By the way, if I'm doing A plus B and B plus A, what is the difference in those? Is A plus B equal to B plus A? I don't know. Is it? I don't know. Let's look at it. We could draw it a couple different ways. We could do A right here, and then B, and then this would be A plus B. Or we could draw B right here, and then A. This is B and A. And so this is also A plus B. So I'm using the tail to tip method for A plus B and B plus A So those are actually the same. So that rule, what's that called? Community. Yeah, community. I think it's community. I'm not sure yet, but math major doesn't know it, physics professor doesn't know for sure, so we're okay. All right. A plus B is equal to B plus A. That's true for numbers. It's true for vectors too. Try this one. We did this one sort of similar before, so we'll just try it again. It's basically the same question. Have a good joke too. So y'all do well. All right, let's stop at 50. 50? Stop at 50? I'll go on to 53. Okay, awesome. C is the right answer. So a pony walks into a bar. This is a bar joke, sorry. But a pony walks into a bar, and he asks the bartender, he says, "Hey, give me a drink." And the bartender says, "What?" He says, "Give me a drink." And the bartender says, "What?" And then the pony says, "Sorry, I'm just a little horse." I love that one. All right, so a possible sum of 12 and 25. You have two options, right? You can have 25 plus 12. What? Somebody outside. Is 37, or you can have 25 minus 12 is 13. So it's somewhere between 13 and 37, which is C. All right, let's do a few quicker questions. And to think about how your vectors are oriented with these, and you probably will have a question like one of these. We don't have a whole lot of these, but you probably have some questions similar. Two vectors are given such that the sum, A plus B, is equal to 0. What can you say about the magnitude and direction of those vectors, A and B? All right, let's stop at 125. 125. Okay, good. D is right. If A plus B is 0, that means that they must have the same magnitude, but they have to be in opposite directions. Equal, but opposite directions. Let's see, that's not really 90%, but it's almost 90%, right? So you get like an old, often used joke. Two atoms walk into a bar, or walk into, I guess it doesn't have to be a bar, but they walk into a bar, and one of them says, "Hey, I think I've lost an electron." And the other says, "Are you sure?" And what do they say? "I'm positive." All right, given that A plus B equals C, and that this relationship is also true, that the magnitude of a squared plus the magnitude of b squared is equal to the magnitude of c squared, then what can you say about these vectors? The vector sum, a plus b, is equal to the vector c, but then also, that relationship given their magnitudes, that's what those lines mean, the magnitudes of the vectors, a squared plus b squared equals c squared, what does that tell you about those vectors? How are they oriented? All right, let's stop at 110. 110. A is right. They're perpendicular to one another because that relationship is called the Pythagorean theorem. Right, so this is the Pythagorean theorem. That means that the vector A and the vector B are like this, and then the vector c is like this, such that a squared plus b squared equals c squared. That has to be true, but they have to be perpendicular to one another. You're going to use the Pythagorean theorem for this part, for the test, when we actually are adding vectors. All right, given that a plus b equals c, and that a plus b equals c, how are they oriented to one another? So the vector sum, a plus b equals c, but then also the magnitudes add up, a plus b equals c. So what does that tell you about how the vectors are oriented with respect to one another? And many of you have the right answer right now, but about 7 or 8 of you don't. So ask around. What's your neighbor put? All right, let's stop at 1 minute. Just 5 more seconds. Look at that, B is right. Because in order for both of these things to be true, we have to have it such that A plus B equals C. That's the vector A. The vector B is equal to the vector C. That's using the tail to tip. But then also that their magnitudes, like let's say that this is 2 meters, this is 2 meters, so this would be 4 meters. So they have to be oriented in that way in order for that to be true. Because if they were any other way, like if they were oriented like this in a right triangle, this would be 2, this would be 2, this would be the square root of 8, right? Square root of 2 squared plus 2 squared. It's going to be some value less than 4. Anytime they go away from being parallel to one another, the sum of them is going to be some value less than the sum of the magnitudes. They have to be parallel and in the same direction. Okay, we'll come back to this. Now let's look at the components of a vector. So what you're going to see on the test, you'll see 3 or 4 questions that deal with vectors. 2 of those questions will be consecutive. You're going to see one of the arrows. And I'm going to ask you, what is A plus B? What is B minus A? You'll have 2 vectors, and I'll ask you to do the sum or difference of those 2 vectors and show graphically what the result is. Then you'll also have some conceptual questions, kind of similar to the things that we've seen here today. Then you're going to have some calculation problems where you have to find either the components of the vector, and then you'll also have one where you're going to have to add 2 vectors, one of which is off axis, and we'll do one like that. But first let me show you how to find the components of the vector. If I have a vector A, and vector A looks like this. It goes from the origin up to some point. there are projections of that vector onto the x and y axes. And we call those projections the x and y components. You can think of it as a shadow. I like to think of it as a shadow. That if you have like a big shining light on this side of the arrow, then it's going to cast a shadow of this vector onto the y-axis. And then similarly, if I have a light shining down from above it, it will cast a shadow along the x-axis. If you drop down from the tip of the arrow, you'll drop down to the x component. You're going to do that in the lab where you measure those graphically. But on the test, I'll expect you to be able to calculate them. And you probably recognize this as a certain shape that we talked about already, that it's a right triangle. In fact, I can redraw this. If I take AY, I can actually draw it over here. And I will here in just a second. So my vector A, which is this vector right here, is going to equal to the vector sum of AX plus AY. And we're going to learn how to do that, how to take the vector sum. It's using skills that you already know, so it won't be that big of a leap. So as we talked about already, like let's say, for example, that AX and AY are like this. Now let's say that AX is 3 units long and AY is 4 units long. That means that the vector A is going to equal 4 plus 3, 7 units long. Right? Right? No, that's not right. Right, so that's not the case. Because when you're adding up vectors, you don't just add numbers. Right? It's more complicated because, you know, I don't know why. Because it's physics, I guess. It's just the way it is. What? I don't want to hear anything from you. No, because it's just vectors, man. You just got to know how to use vectors. Okay? So let me show you how to do that. First thing we want to know is how to calculate the components of those vectors. As I said, we have a triangle here. It's a right triangle. This is my vector A over here, and then I have my x and my y components. Remember your SOHCAHTOA, the sine of the angle theta is opposite over hypotenuse. And so if I have my triangle with A, theta, AX, AY, then I would say the sine of theta is opposite over hypotenuse. That's going to be, it should be AX right here, y'all. It should be AY over A. And so that's where this expression comes from, that AY is equal to A sine theta. And then you can do a similar thing where you do the cosine of theta. So ka is adjacent over hypotenuse. And so that's equal to AX over A. And so AX is equal to A cosine theta. Now I know I told you that there are only 2 equations that you need to know, those 2 kinematics equations, but that's not entirely true. Like you need to know your sine, cosine, and tangent functions and your quadratic formula. But I just consider that something that you know, like muscle memory, right? That you have that down. But if you don't, you need to get that. You need to learn it because you're going to use it a lot this semester. Your right angle trigonometry that we had in chapter 1. But also these extra expressions where we have AY equals A sine theta and AX is equal to A cosine theta. That's something that you'll use a lot this semester. So just commit them to memory if they're not already. Like if you don't know your trig functions so well that this just sort of falls out naturally. This is sort of dependent, and we'll see some very special cases in this class in chapter 4 where how do you measure your angle theta. You can probably see this, that if I measure my angle theta up at that vertex, then I'm going to get a different response because my adjacent and my opposite sides switch. But almost always in this class, always in fact, almost always, we'll measure our angle theta from the x-axis. That's sort of the standard thing to do. And when you measure your angle theta from the x-axis, these expressions are always true for vectors. I like to remember them because they're alphabetical. X and then Y, C and then S. Does that help you? or you just remember something, I don't remember the definition, but X and Y, C and S, that they sort of follow the same alphabetical order for the cosine sine X, Y components. We will not do Z components, though you can do it. It's a little more complicated, and certainly y'all can do it, but we're not going to do any Z components. Actually, Z components aren't really more complicated at all. That's how you find the components of the vector. We're going to skip this little section right here. It's important, but it's not important until we get to chapter 4. And so as to not overload you too much, we're just going to skip that little section, just down to where the line is, about rotating the coordinate system. Okay? Let's look at this. So I have two vectors I want to add, A and B. Pull out your colored pencils. Let's say that the vector A is here, and the vector B is here. And listen, you're going to have to do this for your test. You're going to have to take two vectors. One is on axis, like vector A. One is off axis, like vector B. And then you're going to have to report what is the magnitude and or the direction of the resultant vector. I could ask either. I will have given you some angle for vector B. That's how we describe the direction of vector B. And then I'll want to find the magnitude numerically, like you need to know how to do it graphically, but numerically for the vector R, where R is equal to A plus B. Now you might be able to imagine what you would do here. I would find AX. This is AX. And in this case, since A is on the x-axis, it's going to equal AX. In fact, there is no y component for the vector A because it's on the x-axis. There is no shadow on that y-axis. And then vector B, BX, right here. And then I do have a y component, BY. And so, in short, what we're going to do is we're going to take the sum of these x components and the sum of any y components that we have, and they're going to become the components of our new vector R. I'm just laying it out for you. I'm going to go through all these steps in just a minute. And it might look like there are a lot of steps, but trust me, after you've done it several times, it'll be a lot easier. So I hope that over the weekend you'll go back and look in your homework or look in the old test and work through some of these. Okay? I would really recommend that you do that before Monday. That way, if you have any issues on Monday, we can deal with them. So the vector R is also the sum of its components. It's going to be equal to Rx plus Ry. And Rx is going to be AX plus BX. And Ry is going to be AY plus BY. This is the x component of R. It is the sum of AX and BX. It's like I wrote here. That should be an X. This is the y component of R. It is equal to the y components of A and B. But in this case, there is no y component of A. So AY is equal to 0 for us. But as for a general rule, this is true. Notice I haven't drawn arrows here. These are just sums. I'm just adding up the numbers. And I'll do one with numbers for you. Then once I get that, or let's do an example. Oh, wait, no. No, that's fine. Let's do an example. I think it'd be better for you to see one. As an example, this one's going to be a little more complicated than the one you'll see on your test because both of these are off axis. They both have directions. But the process that you go through is still the same. I always like to draw a picture first. It always helps me to draw a picture. So then I know sort of roughly what the answer is going to be, and I can at least tell which quadrant the vector is in. So vector A is 1 meter long and 45 degrees from the axis. I'll draw vector A in red. And then vector B is 2 meters long and 60 degrees from the axis. So it's looking like this. Shoot. Let me redraw it. Oh, Ran out of space here. Draw my vector. This one's shorter, this one longer. All right, so this angle is 45, and this angle right here is 60 degrees. So I know that my vector r is going to start here and go up there. So you know what, sometimes on your test, you can, always on your test actually, you can get rid of some answers if it's a direction, especially just by drawing a picture. Because I know if I have an option that says 120 degrees, that ain't right. Or if it says 280 degrees, that's not right either, because it has to be in the first quadrant. In fact, I know it has to be more than 45 degrees just from looking at this. It has to be between 45 and 90 degrees. So my first step is to find the components. AX, A cosine theta, A sine theta, B cosine theta, B sine theta. Listen, if you have your calculator, just make sure that you're getting the numbers that I'm getting, at least on one of these. You don't have to calculate them all. But you'll need to have your calculator in degree mode. But in calculus, sometimes you guys have to put it in radian mode. So just be careful of that. You might have to switch back and forth. I don't know, y'all in Calc 1, right? You might not go in radian mode just yet. But just be careful with that. So here, my A cosine theta is going to be 1 meter cosine of 45. We're going to be 1 meter sine of 45. And these are both going to give me 0.71. 0.71. And then Bx and By are going to be 2 cosine 60. Cosine 60, MCAT folks, is a half. That's a nice, you need to know that, like for the MCAT. So that's equal to 1. And 2 sine of 60 is, it's like 0.86, I think, is sine 60. This works out to be 1.7. So make sure that you get at least one of those. Just try one on your calculator. All right? Now your next step is to add the components. You calculate the components, then you add the components. You say AX plus BX, AY plus BY, that's going to be 0.71 plus 1, and 0.71 plus 1.7, which is 1.71 and 2.41. I know I'm not keeping proper sig figs, but just bear with me. I'm just going to keep more than I need right now. So what I've done here is I've calculated Rx and Ry. So if I were to draw this on my coordinate system, Rx would be 1.71, Ry would be 2.41, and so R would look like this. There's R, Ry, Rx. So I've gotten rid of those vectors A and B. And again, I know this might seem a little overwhelming, but trust me, you do it 3 times this weekend. You know the trig, you're just sort of applying it to a new situation. Do it a few times today or over the weekend, you'll be okay. I find the magnitude of R from the Pythagorean theorem. So that's going to be the square root of 1.71 squared plus 2.41 squared. That's equal to 3.0. And then if I want to know this angle theta right here, I use my trig function. The inverse tan of opposite over adjacent, that's going to be Ry over Rx. Inverse tan of 2.41 over 1.71. And that's equal to 55 degrees above the x-axis. So your steps. You find the x and y components of the vectors, both A and B. Then you add the x components of A and B, and you add the y components of A and B. If you have one that's in a negative direction, then you'll subtract them. Then you use the Pythagorean theorem and your inverse tangent to find the new direction and magnitude of this sum, the vector r. Instead of doing another example, why don't we turn to the back and we'll do one that's a sample for you guys. I know that you probably don't have it just yet, but just to get a little leg up. And then we'll do some other examples on Monday. Pretty sure I have one in the old test. Oh yeah, look at here, I do. Number 25 on exam 1. I want to know the magnitude of the sum of those two vectors. Your test will look very, very similar to this. Draw a picture, find the x and y components, add the x components, add the y components, and use the Pythagorean theorem to find the magnitude. While y'all are doing this, I'm going to draw a picture. Yeah, Rebecca. Oh, really? Do you remember what it was? Well, even if I write it down, y'all are going to know which one it is. Well, shoot. Everybody just put A. We'll work through it. Or y'all go ahead and... I could change all of them. But then she might tell me the wrong answer. Everybody put A. But y'all go ahead and work through it, and then I'll work through it with you. I'll give you a few minutes to work through it, and then I'll work through it with you. Everybody's put A. I'm going to close this out here in just a moment. Just a few more seconds. 2:05, I'll stop it. Hey, good job. All right. First step, find the x and y components. A is easy, right? AX is 11, AY is 0. BX is going to be 24 cosine of 60 and 24 sine of 60. Y'all know what those are? What's the first one? What is it? Oh, it's 12, right. What's the next one? 20. I'm just going to call it 21, okay? So that's my BX and BY. So what I've done is I found AX, I found bx, and then I have by. So now I'm creating this new triangle that's going to have sides 11 plus 12 and 21. And so now I'm almost there, right? This is equal to 23. So I do the square root of 21 squared plus 23 squared. And I don't know what that is. Does anybody know? 31. I thought you told me that wasn't there.
On the video, it was 39.
Is this right? 21, 23? Did I make a mistake? I have to go back and look at that. That's right, Savannah? I don't know.
In the video, you just had tomato adding.
Oh, okay. So the test was right, the video was wrong. Okay, I'm sorry about that. I'll try to go back and make a note. Yeah, y'all have a great day, okay? Please do look at this weekend, please.